With the development of the Internet of Things, devices which work alone can communicate each other and exchange information through the Internet, but may suffer data theft or attack through the Internet. Thus, a secure mechanism is needed to protect devices and messages. The TrustZone technology can achieve the IoT security requirements. The following will introduce ARM TrustZone technology and show the example of how to program TrustZone on M2351. Computer firewall isolates the Internet to internal and outside network to protect internal network information from not being attacked by outside network. The M2351 with TrustZone technology also partitions microcontroller hardware into secure and non-secure world to protect important secure world information from not being easily stolen or modified by non-secure world. Non-secure world cannot access secure world data easily unless the access is certified by secure world. So the important data which needs protection can be saved in secure world safely. By partitioning hardware into secure and non-secure world, TrustZone technology can achieve the security requirements. TrustZone partitions memory map into secure and non-secure. Other resources, including flash, SRAM, and peripherals, can also be partitioned into secure and non-secure. Secure world can access all resources, including flash, SRAM, peripherals, and system registers. Otherwise, non-secure world can only access non-secure resources. In order to partition system security, memory address security attribution can be configured by IDAU and SAU. The security result is the higher security compared between IDAU and SAU. The security attributes of memory map address can be configured into secure, non-secure, or non-secure callable. Secure code runs in secure memory map. Non-secure code runs in non-secure memory map. Non-secure callable entry function is located at non-secure callable region. Non-secure code can call secure function by non-secure callable entry function if secure code allows the access authority. In M2351, IDAU partitions a fixed memory map security attribution. The address bit 28 is used to define security. If the bit 28 is 0, it is secure. In flash and SRAM, code can be executed. It is non-secure callable. The first 2 KB of flash is fixed to secure. If the bit 28 is 1, it is non-secure. The system and debug-related registers are not fixed to certain security. They are determined by current system state. Users can set their own security attribution configuration. If SAU is disabled, the whole memory map can be set to all secure or non-secure. If SAU is enabled, you can set certain address range security as non-secure or non-secure callable. Other address not being defined is secure. After configuring the security attribution, secure program runs in secure memory map and non-secure program runs in non-secure memory map. System starts up as secure program. The system can switch between secure and non-secure state through function call. If non-secure code calls secure function, function A. Non-secure code calls non-secure callable entry function, function A entry at first. The first instruction of non-secure callable entry function is SG instruction. It is the entry point where system switches from non-secure state to secure state and then calls secure function, function A. Secure function ends with BXNS instruction and system returns to non-secure state. If secure code calls non-secure function, function B, Secure code uses BLXNS instruction to call non-secure function. Before switching to non-secure state, the return address will be stored in a secure stack, and LR value is set to a special value, function return, then calls non-secure function, function B. Non-secure function ends with BX instruction branches to address LR. LR value was set to the special value, function return before. Then system switches back to secure state. The following will show TrustZone programming on M2351. The development environment is Kyle MDK and Nuvoton New Link Debugger. First, this video will introduce how to configure security attribution, including memory map, flash, SRAM, peripherals, and peripheral interrupts. After setting security attribution, configure related secure and non-secure project settings. Compile and download program. You can observe the state switch between secure and non-secure through debug mode. Open M2351 TrustZone sample code. The Kyle project provides configuration wizard to help user configure security attribution. Click Secure Project, then User, and select the partition M2351.h file. Then select Configuration Wizard page. To configure memory map security attribution, in Secure Attribute Unit Control item, select Enable SAU. In Enable and Set Secure Non-Secure Region item, specify the start address and end address, and set the region as secure, non-secure callable to place non-secure callable entry function. Set secure flash and SRAM size. In Peripheral Secure Attribution Configuration item, configure peripheral security. For example, set UART1 as non-secure. In Assign Interrupt to Secure or Non-Secure Vector item, configure Peripheral Interrupt Security. For example, set UART1 interrupt as non-secure. Configure related secure and non-secure project settings after setting secure attribution. Under the secure project, click Options for target. On device page, select M2351. On target page, select software model to secure mode. On linker page, edit scatter file. Specify secure flash, SRAM, non-secure callable entry function location, and import the non-secure callable function library. On debug page, select Download and Debug Tool to Nuvoton New Link Debugger. Under the non-secure project, click Options for target. On target page, select software model to non-secure mode. On linker page, edit scatter file. Specify non-secure flash and SRAM location. If non-secure code uses non-secure callable function, which is provided by secure code, add the non-secure callable function library, which is just imported in secure project. After compiling and downloading both secure and non-secure code, under the secure project, click Start Debug Session button to execute the secure code. secure code is executed at first. To add non-secure code, under View menu, click Symbols window, Non-secure, and main.ns.c, and then right-click on main and select Show Code for main to open non-secure code. To observe system state switch, use new vertical tab group function to place secure code in left window and non-secure code in right window. After setting breakpoints in non-secure code, click Run. Then, code is executed to non-secure code. If user wants to call secure function in non-secure code, non-secure code configures sysdig and enters sysdig interrupt periodically. In sysdig interrupt, non-secure code calls secure function, secure LED on. This is secure function, secure LED on. Click Run. Then enter sysdig interrupt and call secure function. Non-secure code will call the corresponding non-secure callable entry function. The first instruction of non-secure callable entry function is SG instruction. Then, non-secure code can call secure function, secure LED on. Then, execute secure function. Secure function ends with BXNS instruction and system switches back to non-secure state. If user wants to call non-secure function in secure code, secure code also configures sysdig and enters sysdig interrupt periodically. In sysdig interrupt, secure code calls non-secure function. Click Run. Then enter sysdig interrupt and call non-secure function, non-secure LED on. Secure code saves secure information and switches to non-secure state with BLXNS instruction. Then execute non-secure function. Non-secure function ends with pop instruction. Get return address value and system switches back to secure state. TrustZone technology partitions microcontroller system hardware into secure and non-secure. Non-secure cannot access secure arbitrarily, so important data can be protected safely in secure. If users want to release authority, they can add software certification method. The IoT application can be implemented safely and flexibly.